All right, well, it's 1:10, so I'm going to start. I'm going to close the door. I mean, I'm loud, but I can't be louder than an entire group of people. Hi, I'm George Neville Neal. This is a policy talk, which means I get to rant instead of actually talking about science. So that's fun. Although I will be talking a little bit about science. So open source for open science, which might make you ask the question, why would science need to be open? And so this is open science is a thing from UNESCO, which is part of the UN, which we'll talk about in a minute. But I basically came up with this talk because I had been talking to someone about this particular topic, about open science. So, quick refresher about the scientific process. So, for anyone who's not a scientist, this is how science is supposed to work. You have a question, form a hypothesis, you test the hypothesis, you analyze the results, and then you tell the world. And so it was very strange when I saw this very long document, which I do not recommend reading, from the United Nations, talking about how important open science was to the world and how this was something that we really needed to care about. And all I could think was, well, but if you don't do this, then it's not science. You're just in your basement making experiments. So why do we need open science? And what happened to science that made it not so open is that. So until 1945, pretty much every single scientific result that wasn't used or kept secret, which was a very small number of them, was published. In fact, as I'll show you on the next set of slides, leading up to this little event, or big event, that's Big Mike, all of the science that was involved in what is now big science was open. So these are images from something called the Physical Review. Physical Review is where all of the science that went into the atomic bomb and radar and pretty much, and not computers, pretty much everything physics that you depend on and that makes life as we know it possible, was actually published. None of this was ever secret. But since the point of, atomic bombs, a lot of it has been. And so the last 50 years, we've spent actually siloing science. We've taken science and we've hidden it. And this has had some really negative effects on society, which we'll talk about in a minute. But it didn't always used to be this way. So note, it's hard to read here, but September 1939, right? So at that point, Leo Szilard convinces the US government that all of this stuff should be secret. So this may sound a little familiar. Heard about these guys? So all of the companies who did closed source right up to the LLMs have also decided to keep everything secret. OpenAI will let you use their system. They won't tell you how it works. In fact, as far as we can tell, they don't know how it works, but that's okay. It's magic. So we have this now 50-year history since the end of the Second World War of making science by default not open. Certain things are open, but not everything is. And this has other negative effects. But, of course, there's always counterbalancing things. And we're at a conference that's all about that, right? So, and Jupiter is sort of the closest to science. Conferences like COSCUP and all of the open source projects are the opposite of closed, right? The point is to come here and talk about what we work on and to talk to other people. And that's the actual scientific process, right? So one of the beauties of open source as a software system and as a computer system, and we'll get to the science part later, is that you're sharing your results. And that's what scientists have always done. Like Faraday and all of these other guys, they didn't just go, oh, I have a thing. They're like, I have a thing, here, try it yourself. And in open source, we do the very same thing. And so open source is really in the right place to help with open science. So let's talk a little bit about what open science is and what these people were talking about. So it's this UNESCO recommendation. This is actually the most readable part of the recommendation. The rest of it is 50 pages of design by committee documentation, which I do not recommend reading. I read it. I don't. Just know that it's useful, and it's something they're promoting. So what's interesting is, in these recommendations, if you've never read a UN recommendation, I really don't recommend it, they basically say member states should, right? Which means all the countries on Earth. So these recommendations are being pushed on all of the member states. And the idea is that, well, open science increases scientific collaboration, makes multilingual scientific knowledge available, and opens processes. And actually, in this documentation, open source is called out specifically, because open source is the only chunk of software that really is in the same vein as the scientific method, right? So, interesting thing to note. Note the date. So that was 2021. Why are people suddenly talking about open science now? This is why. This is the world outside. And so for those of us who work in the sciences, these lunatics have now made life very difficult. To be honest, when I started in the sciences 40 years ago, so I started my undergraduate 40 years ago, I never thought I would live to see the day that there would be protests for science. Like, people actually go out in the street and protest in favor of not dying of diseases. It's a very strange world. This is why UNESCO has pushed this open science thing, because of all the things I talked about earlier on, secrecy, making it difficult for people to understand science, and because scientific literacy is not on the increase, people don't actually understand how it works. We now have people who can believe, well, whatever they want. And that's been a really big problem. And so the push for open science is really a push for science generally. And we, open source, can be part of that. I do love this, by the way. Science is real. Yes, you didn't die of a cold because science is real. So science and open source have a shared culture, right? We have a commitment to openness, to sharing results, to, well, we say try to reward excellence, but there's been a lot of shenanigans in science recently, if you look at papers that have been pulled from publication. But most importantly, burden of proof, right? So in open source, someone says, well, I want to do this thing, or I've done this thing, and we're like, show me the patch, show me the source code. And in science, someone says, I have a machine that does cold fusion, which was a thing back when I was a kid, which turned out not to be a thing. And all the other scientists say, show me, right? Burden of proof. And so we actually have some really good bits of shared culture between the sciences, capital S, and open source. So open source needs open science. Like, for this thing to succeed, for UNESCO's ideas to succeed and to push science generally on the planet and prevent ignorance from destroying us, science needs these tools, needs us to help them with these tools. I'll talk about that more in a bit. So it's mentioned in section 7, paragraph D of this document. Really, don't read this document. And open science, the open science people need us for a few reasons. One is commercial tools often miss the mark. So if you talk to scientists, and one of the things I've been doing over the last 6 to 9 months is talking to physical scientists, chemists, physicists, biologists, and you say the following question to them: tell me about your use of computers. And they always say the same thing, which is, oh, it's terrible. Really? 10 minutes? Anyway, they do. They all say the same thing. In fact, a biologist I talked to, she's great. She's studying Lyme disease, which is this disease is becoming more prominent as we sort of encroach on the natural world. Ticks, these little bugs give you Lyme disease. And I said, tell me about your use of computers. And she said, oh, it's terrible. And she had this long list of, non-interoperability machines that don't, that do like actual tests on tissue that don't output data they can use. Just all of these great things. Then I talked to a chemist, physical chemist, and he said, well, there's one piece of software, but the company got bought, and we don't know what's going to happen to it, right? And so this is another place where open source can really help in the sciences. It's been fascinating. Like, this has been my most favorite, like, non-computer sciencey thing to do, is to just find these scientists. And usually they're just friends or friends of friends, spouses of friends. At one point I was in a bar. That was weird. And wound up talking to someone next to me who turned out to be a geneticist. And I said, oh, tell me about your use of computers. Oh, it's terrible. So commercial tools miss the mark. In fact, most commercial software, if you think about Excel or like things that maybe we don't use because it's closed source, it's meant for bankers, right? But people have taken that to do science. So the chemist who I talked to was like, oh yeah, we just do everything in Excel. I'm like, does that work? No, but well, we can get a paper out of it. It's not very good. And then we have a challenge on our side, which is in open source, we have for the last 50 years. Open source is almost that old. I mean, if you consider before the FSF, when we did public domain software, which is the first software I ever published. When we write software, the collective we at conferences like this, we're really interested in the computer, right? We want to make the computer do the thing. I write operating systems. I am all about making the computer do the thing. Usually making the lights blink and the packets go, because that's what I do. But that's not what the people who consume software, and it's certainly not what scientists want. Right? What a scientist wants to do is to analyze the real world and apply the computer to that, and then come up with, and then test their hypothesis, that whole scientific method thing. That's what they want to do. And the amount of software written to do that is minuscule. There are very, very, very expensive pieces of commercial software to do very narrow bits of science. Genetic assays, chemistry, chemical analysis. And then the other challenge is we have a silo problem. So people either use, if they don't have money, they use whatever's they've got like on their computer. So they're using Excel because it came with the Windows box that they were given at work. Or they're lucky enough to work at some place like CERN or a big physics lab where they have a whole team of nerds like us who are there just to make their experiment work. And I saw this really great talk at CIDR in January from the woman who runs the entire computing group for the people who found the Higgs boson, right? The big physics experiment. And she did this great talk about like how they can see like particles in the first few nanoseconds. It's amazing. And none of her software can be shared because it only works for her experiment, right? So you either have people using poorly targeted commercial software or poorly targeted open source, right? They'll run Linux or BSD or Apache or Jupyter Notebooks, which I mentioned as a way of doing science. But those things aren't meant for scientists. They're meant to make the computer do the things we like the computers to do. So, maybe we forgot something. So one of the other problems in software and in our software, and one of the challenges we need to overcome to do open source for open science is the world is not binary, right? So computers are these simulations. And I think computer scientists, and I am guilty of this, often forget that, right? But if you think about, these are the things people want to analyze, right? Climate. Oh, by the way, this is Ali Shan. I found a picture of Ali Shan. I was very excited. No one else, if I ever give this talk outside Taiwan, will know what that is, but we all do. So T, the ocean, climate, plants, whatever. The Earth is not binary, and what scientists care about, physicists, chemists, biologists, these people, none of that data is binary. Even when people do genetic analysis, and they're always like, ACT, like the letters in the genetic analysis, it's still not binary data. And so computers aren't well suited, and our software is not well suited to helping those people. If we help those people, we'll all live longer. So science is a means to understand reality, and reality is really messy. In fact, reality is almost all made up of reals. Temperature, pressure, distance, velocity, anything you ever took in a science class before you got out of high school or college is not binary data. Computers are just simulacrums of that, and science needs high fidelity. Most programmers don't understand floating point, which is a big problem. There's a great paper on that. So what does this mean for software? So if we're going to make software for the sciences, which is what open science needs, we need to be able to deal with real data from the real world. And the first thing that most systems do when they take in data is they turn it into some sort of cheap binary format. We don't want to do that, right? What we want is to be able to actually work with real data, reals, as in floating points, like high fidelity data about whatever the person who's actually doing the study wants to know. And another thing that we often leave out, and is only becoming important now, is this thing called provenance. So provenance is, where did the result come from? So if I do, for instance, a chemical analysis, and I started with these 5 chemicals, and I did this mix, and I got this result, and I got another result, and on and on and on down a chain, I want to be able to know that I started here and I ended here. Most computer software is only cares about now, right? What is the state now, not what was the state before. We'll store data in log files, but the idea that you would be able to go backwards in time and know the state of the system 10 steps ago is not something often designed into software. There are people now in the last 10 years working on this, in part because computers have become big, fast, and cheap. Like, how much data could you store in a mainframe in the 60s? Not very much. You could basically do, you could store one chunk of a calculation. Now, I mean, if anyone's wearing an iWatch, you have more data in your iWatch than any mainframe had in the 1970s. So now we have the capability of doing provenance, but our software isn't designed for it. Our software is only designed for knowing about now. But scientists care about the past, because in order to do the whole scientific method trick, you have to say, well, I had this theory, I had this data, I changed this data, I changed it again and again, and this is the result I got. And then from the result, you have to go backwards. So provenance is super important. And then, of course, understanding a scientist's workflow. So many of us here are computer scientists. When you have to put scientist at the end of computer, you may not be a scientist. We're mostly engineers. In science, so in engineering, what do engineers do? Well, good engineers solve problems. We build bridges, we make it so buildings don't fall down. We apply science. But a scientist starts with the question, like something ridiculous, like why is there air? But sometimes it's something less ridiculous. And so understanding how people who do those sciences work is really important. And this is something, again, that's challenging in computer science, because we don't talk to people very often. But we're going to have to make this work. This is why I've been asking all these crazy scientist questions. So, where does the idea start? And then asking them, so imagine you were trying to solve a problem and you didn't know how their process worked. How do I get from A to B, right? I mean, it's not like Einstein woke up one morning and was like, oh, by the way, relativity, right? He wrote down a bunch of steps. And actually, if you want to see this in action, and you have a lot of free time, go find Faraday's The Life of a Candle. So in the 19th century, when Faraday was studying chemistry, he had these amazing notes. And it really shows, like, he was trying to understand how fire worked. Like, how does fire burn? And he worked it out. And it's really impressive. And it's very different than what we do. So, I figured I'd go check and see about open source software for, science. And so I asked GitHub, the knower of all open source and the source of ChatGPT's terrible, terrible suggestions. And I said, okay, well, physics, chemistry, and biology is on the left. Show me the most popular repos in all of these areas. Very few of them have anything to do with science. If you ask about physics, you get physics engines. If you ask about chemistry, it lists all the papers. Someone basically put a thing for their class, and they're like, oh, here's all the best chemistry papers, and then everyone starred it because every student who has to take chemistry looked at it. Very few of these things, I looked through the top 10, are about actually doing science with open source. They're about doing other things. And so, you know, what do we do next? So we have this unique role. People who work in software are at least educated somewhat in the scientific process. We all, if we went to school for computer science, had to do some physics, some chemistry, some calculus, not my favorite class. So we already kind of have this idea about the scientific method, even if we're not always applying it. And also, everyone uses computers. We have convinced the entire planet to use these absolutely ridiculous, faulty, terribly built machines. But they work, sort of. And also, most people use open source. So if you look at least in the United States, I haven't looked in Taiwan, if you look at the national laboratories, the people who do big physics, they're all using some form of Linux or some form of something open source to do their work. And they're using these things. Is anyone here from the Jupyter Project? Okay, good. I like the Jupyter Project. I really, really like the idea. I really want to have a long conversation with them about how notebooks work. But I don't have time. But tons of people use open source. People are using these Jupyter notebooks in science all the time. Guess what Jupyter notebooks lack? Provenance. They can't go backwards. They're just basically calculation machines. It's like having a very big graphical calculator in front of you. So we're in this spot where we, open source, we're at an open source conference, open source people understand how open source projects work. People have computers, people use open source. Now we have to work with them to build what they need. We've spent 50 years making computers work at all. I mean, like if you think about, let's see, it's 2025. A computer in 1975 probably had a 90% uptime. Microcomputers were hand built. I was 8, so I didn't hand build one yet. So I'm old. I'm not that old. I didn't have hair. I did have hair back then, not now. So you know, we did a great job, and open source really helped. Open source made it possible for a lot of things that were not cheap to be available to everyone. Like anyone can buy an RPi, whatever, and run Linux on it. Great, but that's all about the computer. Now we have to take the next step. Now we have to be about the things people are using the computers for. And we've certainly made it so that businesses can use them, but I'm not that interested. So, of course, it's a policy talk, so this is a call to action. On the left is an email where you can contact some people who are working on this. And of course, the modern equivalent of make a web page is create a GitHub. So it used to be 10 years ago, you'd be like, well, do you have a project? Yeah, we have a web page. So you have a project? Well, now we have a GitHub. And it's empty at the moment, but we're working on it. How would one get involved in this kind of stuff? So, at least in English language publishing, Science and Nature are the two journals. They're usually available through libraries or universities. Science isn't that expensive. Nature is super expensive. I only access it through universities. But the nice thing about, in particular, science, which is done by the American Academy of Arts and Sciences, AAS. The nice thing about science is, while it has full papers that I have no clue, like I open a full chemistry paper and I'm just like, sure, I believe you. But they have summaries. So you can actually look at how people are using or doing experiments in the sciences and think about how we might help them, how we might build software for that. There are science conferences just like open source conferences, and some of them are not crazy expensive, some of them are crazy expensive. I think it's important that we start inviting scientists to talk at open source, to tell us about how they're using what we do. Right, so the talk that I attended at CIDR, which I think you can find online, was amazing because, I mean, I'm a physics nerd. Like, I'm not good at it, but I've liked physics since I was this tall. Physics is cool. And so watching someone explain to me how they're trying to figure out how the universe works while doing computer science, like, you know, I mean, I probably had a stupid grin, like one side to the other. So having people like that come and talk at conferences like this is a really great way for us to learn what they're doing and help them do it faster, right? If we can make science go faster, then we get better stuff, and that's good. And finally, of course, it's an open source conference. We should all be making code. I was actually, so I'm a cynic. I mean, I'm a security person, so obviously I'm a cynic. When I did that GitHub search, I was actually surprised. I thought there would be something. Someone would have done something. But nope, not there. So it's time for us to get involved. That's my talk. Questions? Ooh, and I've got 5 minutes. Yes?
You just mentioned Jupyter. Is there a Python one?
Yeah, so IPython became Jupyter Notebooks.
Okay.
Same thing.
Can you, because time is running out, can you talk about most exciting thing you see in the Jupyter project? Because it's really big project and it using scientists and even commercial.
So the thing to me that's interesting about Jupyter and is both exciting and super frustrating is that they want to be a notebook. But here, let me show you a notebook. I don't have a projector. Oh, this one's blank. This is the new one. You notice this is this kind of paper?
Yes.
All of my experiments go in this. You can't do that in Jupyter. The cool thing about Jupyter is it gives you this visual interface to like, oh, show me a graph, right? Here's my data. But what I really want is, I did this on August 9th at 10 a.m. Here's the experiment I ran. In fact, if you go look on GitHub, there is a set of lab notebooks that if you look up GVNN3, I created a lab notebook template, like a real lab notebook, so that when I do my experiments, because now I'm doing a PhD, I can actually track what I did. And the one thing they lack that I want them to have, hence the discussion, is the ability to go backwards. Right, so right now I run this thing and I get a result, I run this thing, I get a result, and I go down the page. But I can't give you the notebook. I mean, I can, you can run the notebook, but you can't even check it into Git. You can't diff it. Like all of the things we can do with source code, you can't do with a Jupyter notebook. So it's very exciting from a visual standpoint, like you've given someone a visual tool. Because it used to be, you would collect a bunch of data and you'd run GNU plot. And then you would get coffee and you would come back and there'd be a graph. And now, because computers are faster and you have this interaction, that's great. But the lack of provenance, going backwards, that's a problem. Other questions? Now that I've trashed Jupyter notebooks, they're going to find me. Yeah. Oh yeah, I use LaTeX. But LaTeX doesn't have history. LaTeX is just a formatting system. I will now have written 2 books in LaTeX, which is better than TROF, which is what I used before that, and you shouldn't look up TROF. Anything else? Yes?
Regarding your last point, make some code. Let's say scientific conferences around me are all pretty expensive. Any pointers to where a person that can write code but does not know about the specific needs of scientists should look like? Where do I know about the needs of someone who works on it?
So I think there's 2 things. One is you can get the stuff from Science Online free. So I would look at some of it was what I did when I first started doing this. I started looking up, there's 2 things. One, look at Science Online. The other is there are a whole bunch of things in computational X. So computational biology, computational chemistry, well, not so much computational physics, because physicists actually built computers, right? We kind of get them from them. But everybody else is like, oh, that's neat. So if you look at some of the conferences on computational, whatever it is, that's where I've kind of started. I'm lucky enough in that I have a lot of connections into the scientific community, so that's how although conversation in a bar, someone next to me is like, what do you do? I'm a computer scientist. What do you do? I'm a geneticist. Oh, tell me about genetics. So there are a lot of online things, and the major, like there's whatever, there's the International Chemical Society, the International, and actually Physical Review is still online. You can find all of, that's how I got that stuff, but Physical Review is still online. The biologists are a little harder to come by. But yeah, I've just been looking at computational X and then emailing people because I'm a weirdly friendly computer scientist. Other questions? Oh, time's up. Thank you very much.